Hello and welcome to Power System Analysis 2. We are in module 1 and we're going to talk about the load flow analysis in much more details. Previously, we had talked about the basic formula of a load flow analysis. Now we'll start to use the formula to get the answers. Now this class will be talking about a much more approximated way of load flow analysis. So let's get started. Now, this is the we define the problem first of all. Now the just make sure you note these points that assume a certain nominal bus load configuration. That is, you needed to first of all make sure that all the bus voltage and the powers are at their nominal values. Okay. Now then, most probably they should be defined in terms of per unit. So you have to set up what is my base voltage, where base voltage and base MVA, and then to find out their nominal configuration in terms of per unit. Okay. Then we specify PGI and QGI, that is the generated power, real power, and reactive power injected in that a particular bus I at all PQ buses. Remember, we talked about different types of buses. So for the PQ buses, P and Q, the injected power in that bus, the injected both real and reactive power in that bus is specified. What are not specified are the voltage of the bus of that bus and the angle the voltage makes with the reference. Okay, so we specify the generated power and reactive and real power at this PQ bus. This specifies PI and J or IQI at these buses. So we can get that what is that amount of power that is being injected. So here we are not taking a PQ bus. We are neglecting what we are not considering the loads in that buses. So whatever the injected power, that is what is the generated power. Let's say a generator is connected to PQ bus. Only that PGI is becomes equal to PI and QGI becomes equal to QI. Okay. Now we have this is for the PQ bus. Now what about the PV bus? PV bus will specify the PGI, that is the generated power in that PV bus, and the voltage at that bus, that is in modulus Vi. Modulus why modulus? We are only considering the magnitude. Now this is the remember these are the values that we start with before doing the problem. So when we have a bus system, we have generators connected to that buses. Okay, so the PQ buses, we need to specify what is the generator uh, real power and reactive power injection. And for the PV buses, we need to know the real power as well as the voltage at that buses. Now we are left with the slack bus, and if you remember, slack bus we specify the voltage of the slack bus and the angle it makes with the reference. Now slack bus, just as a normal circuit, it is the reference bus or reference node. Hence the voltage is taken at a 1 per unit and the angle is taken as 0. So delta 1 becomes equal to 0. So then we find the vector y, which is 2n number of variables, where n is the number of buses present. Okay, so y is the primitive admittance we found out. Now this 2n variables can be solved iteratively to determine the values of the 2n variables of the vector x comprising of. So when we solve this 2n variables, why these 2n variables will solve for the powers as well as for the real and for the reactive powers. Okay, so when we solve them, we determine certain vectors. So we'll determine the voltage and the angles of the PQ bus, reactive powers and the angles of the PV bus, and active and reactive power at the slack bus. So these are the values we need to find out after solving. Now after we solve these values, then we can find the line flow. So we can find out that from bus 1 to bus 2, what is the power flow from bus 1 to bus 2 and bus 2 to bus 5, whatever. When the buses are connected, what are the power flows? So let me recap this. So you need this PQ bus, the P and Q being specified, PV bus, the P and V being specified, and the slack bus V and delta being specified, and then you solve it to find out these variables, that is the voltage and the angles for the PQ bus, reactive powers and the angles for the PV bus, active and reactive powers at the slack bus. Okay, and next part is to find the line flows. Now we'll start, as I've told you, we'll start with an approximate load flow solution. Now, how can we approximate our load flow, and why do we approximate our load flow? As you have already you have found out that it is a very complex equation to solve. Hence, the approximation makes the equation easier to compute. Now, how do can we do this approximation? And well, whether this approximation is good for like if we approximate, will it give me a good result? It will give you a good result if you approximate properly. How do we approximate it? Is that we neglect the line resistance, okay, and the shunt conductance of the overhead lines. Those are neglected. What are shunt conductance? The capacitance, the line capacitance for the overhead line, that can be neglected. So we line resistance, why it neglected? Because we are using aluminum or copper, which have a high uh, conductance, so resistance is pretty low, and, and more than the resistance, the inductance of the lines are much more prevalent. So we can neglect the resistance, and if you neglect the resistance, the equation becomes much more simpler. Okay, so line resistance being small are neglected. Shunt conductance of overhead line are always negligible. That is the PL, that is the load power. The power loss, active power loss is zero in the system. So PL, the active power loss, is taken to be zero. Now what is this? Why it is taken to be zero? Active power loss is nothing but the I square R loss in the power system, but we are neglecting resistance. That means we are considering R to 0, so it becomes PL equal to 0. So what we have is that theta ik is 90 degrees. That means what? And theta ii is minus 90 degrees. That means we are considering only inductances. We are considering only inductances. Okay, when we considering only inductances, the angle becomes 90 degrees. The angle of uh, the admittance become 90 degrees only. Okay, next part is that the change in the angle of the voltages is is not very big. Okay, now if it is small, less than pi by 6, what is pi by 6? Is less than 30 degrees. We can consider sine theta I minus theta k as equal to theta I minus theta, sorry, delta I minus delta k. Delta are in terms of radians. So we can neglect this sign, and we can easily replace this sign with the radians itself. Okay. Now this is justified consideration of stability. Uh, if this what is if you remember this delta, and I think you have learned about the string equation. Uh, this delta is important in terms of stability. So this consideration is also important, because we cannot allow delta change to be a lot, because that the amount of delta change, that is from delta from one bus to the other bus, the change in delta, if it is big, that change of delta determines the amount of power flow from one real power flow from one bus to the other. If this delta is big, uh, the power flow becomes big, but after some time, after a big amount of change in the delta, the there will be a drop in power, and the uh, system will go unstable. So I'll just explain very briefly. Just one second. Okay, so let us have, this is delta and this is the power. Okay, so the power flow between these two buses depends on the delta. Now, let's say we are talking about bus 1 to bus 2. The power is flowing from bus 1 to bus 2. This is 1 and this is 2. What happens is that as you slowly increase the delta, the power flow increases, but then the power drops. So delta can be at max 90 degrees. But we do not go to 90 degrees because any change, any more change in the delta, the power will drop and the delta will start increasing. So this system will go unstable. So we keep the delta within these couple of ranges less than 90 degree and not go towards this zone of closer to 90 degrees. Okay, so if we are talking about 30 degrees, so it is somewhere here. Delta is in this zone. Okay, so delta is in this zone. So we can say sine of this delta, this is the change of two delta, that is equal to this delta. This is what this delta means. This delta is nothing but delta I minus delta k. That delta is within this small range, so that we can consider these to be like sine can be replaced by delta I minus delta k only. Okay. Then next part are all buses other than the slack buses. That is, slack bus is normally numbered as bus number one. All buses other than the slack buses are PV buses. That is, voltage magnitude of all buses including the slack buses are specified. Now we determine, if we give the values of the voltages for every buses. We are starting to work with our problem. Okay, these are approximation, and we start with this approximated one, so we'll get the result faster. Okay, now if you remember the previous equation now is changed. Here it was a sine delta minus delta k, but it is now only delta I minus delta k. Okay, the qi remains like this. Okay, so here the we have specified all the voltages at different buses. Okay, we have started our solution. We have defined the voltages at different buses. Okay, now these two represent a linear algebraic equation of delta i's, which are n minus 1 in number, as delta 1 is specified at the slack bus, delta 1 is 0. Okay, so we have specified the voltages at I. Okay, then one of the delta is being specified already as 0. The nth equation corresponding to slack bus n equal to 1 is redundant, as real power injected at this bus is now fully specified. Okay, now slack bus, we are the equation of the slack bus will be neglected, because we already know what could be the value of the power, because slack bus, it is basically the total generated and the difference between the total generated power and the total demand power. That's it. Okay, that means what? The power of the slack bus. Remember, the slack bus power and real and reactive powers are not specified. If they are not specified, the equation we will solve for the other buses. Now the whatever is left, we will put that is being used in the slack bus. So the real power of the slack bus is nothing but the total demand minus the total generation. Remember, see, it is I from I equal to 2 to n. So we are with total demand uh, other than slack bus minus total generation other than slack bus, and PL is 0 because we are neglecting resistances. So this becomes the total power of the slack bus. Okay. Now we will solve the this equation. It starts solving is the above equation can be solved explicitly or non-iteratively for different values of delta. So we put different values of delta here. What values of delta to be taken? Now delta one of the delta is already given. Okay, one of the delta is already given, that is delta equal to 0. Other deltas can be assumed and then checked to solve the value of the different real power of different buses. Now when you get the this when you get the pi, you can also get the value of qi using this equation. So this is the approximated load flow. Okay. uh, so this is the end of this class. We'll very soon we'll do a couple of problems on this so that we can understand this better. Okay, so this is the end of this class. Thank you.